In Unit 10, entitled Matrices, we will be dealing with systems of equations. The first section, 7.3, entitled Multivariable Linear Systems, deals with problems like the one you see in front of you. With a system of 3 variables and 3 equations, there is a solution. Finding that solution is not a very easy task. On the other hand, checking whether an ordered triple is a solution to that system is quite easy. We simply need to plug in each of the values, the 9, the -4, and the 2, for the x, y, and z in each equation. If that ordered triple makes all 3 of the equations true, then it is a solution to that system. So by plugging in 9 for x in the first equation, and -4 for the y, and 2 for the z, we check and see if that's true. And sure enough, we get 3 is equal to 3. So that ordered triple does work in the first equation. When we try it in the second equation, you'll see it works there as well. However, in the third equation, by plugging in 9 for x, and -4 for y, and 2 for z, we find out that it does not work in that equation. So therefore, that ordered triple is not a solution to this system of equations. So here's a system with 3 equations and 3 variables. Most students have no trouble solving this. By looking at the last equation, they can figure out what z is equal to. Divide by -2, and we see that z is equal to 1. Now going up into the middle equation, we can plug 1 in for z, and therefore determine that y must equal 0. And finally, after plugging in z equals 1 and y equals 0 to the first equation, we're able to solve for x. And we're going to get x is equal to 7. So the solution to this system of equations is the ordered triple 7, 0, 1. As I've mentioned, this is called an ordered triple, much like we had ordered pairs back in Algebra 1 and Algebra 2. When a system is in what we call upper triangular form, here's an example, it is very easy to solve. We'll look at usually the last equation, solve for that variable, plug that into the second equation, solve for the second variable, and then plug both those values into the first equation to get a solution for the first variable. This process of solving a system in upper triangular form is referred to as back substitution. So if we can take a system and put it in this upper triangular form, we should be able to solve it quite easily. So here's the system. 3 equations, 3 variables. At first glance, there's no easy way to solve this. Before we tackle this, there's a few operations you should be aware of. Basically, there's 3 operations that you're allowed to perform on systems of equations. The first thing you're allowed to do is to interchange any 2 equations in your system. For example, just doing that should not change the solution to this system. The second thing you're able to do is multiply both sides of any one equation by a non-zero constant. For example, if I multiplied the third equation by 2, I'd come up with 2x plus 2y minus 2z equals -2. Replacing that third equation with this multiple of the original third equation still gives us a system that has the same solution. Those first 2 operations should seem rather obvious. It's the third operation that's the most useful. You're allowed to add a multiple of one equation to another equation, and thereby replacing the second equation. I'll show you what I mean in a few minutes. This process of taking a system of equations and using these operations to put the system in upper triangular form is referred to as Gaussian elimination. So you'll see several problems on your homework which will say solve the system using Gaussian elimination. So we're going to use these three operations on our system so we can put it in that upper triangular form, which is easy to solve. Okay, now let's tackle that system that you saw a minute ago. The first thing I like to do is to start with a leading coefficient of 1 for the x variable in the first equation. And I'm going to use some notation so it's easy to look back and see what I did. So I'm going to take equation 1, I'll write that as e sub 1, and switch it with equation 2, e sub 2. So what that'll do for me is have a leading coefficient of 1 in my first equation for x. And at this point, the third equation is still exactly as it was a minute ago. Okay, now the next thing we want to do is we would like to use this 1x in the first equation to eliminate the x terms in the second and third equations. So if I make a copy of the first equation and multiply it by -2, and then add that copy to the second equation, the 2x will cancel in the second equation. Notice I wrote my notation next to the second equation because that's the one that's going to be replaced. So my first equation stays the same. But now if you multiply a copy of that first equation by -2 and add it to the second equation, and if you need to write that on the side on some scrap paper, that's fine. If you can do it in your head, that's fine as well, whatever you need to do. But we'll have -2 times x plus 8. We're going to get a 0x in the first spot. Then we're going to have a 4y plus 4y, which will give us 8y. We'll have a positive 6z plus z, which gives us 7z. And then we'll have a -4 plus 1, which will give us a -3. Now let's worry about the third equation. Let's eliminate the x in the third equation. If I multiply the first equation by -1 and add that to the third equation, the x terms will cancel. So a -x plus x is 0, and then a positive 2y plus y will give me 3y. And then I will have a positive 3z minus z, which gives me a positive 2z. And then a -2 and a -1 gives me a -3. We're almost done now. There's only one more step. We would like to eliminate the 3y in the third equation, and then our system would be in upper triangular form. So here I'm going to combine two of those operations that you saw on the previous page. If I multiply the second equation by -3 and add that to the third equation multiplied by 8, that will cancel the y term in the third equation. So the first equation will stay the same. X minus 2y minus 3z equals 2. The second equation is also staying the same. 8y plus 7z equals -3. But now my third equation, I'm going to have a -24y plus 24y, which will be 0. I'll have a -21z plus 16, which will give me a -5z. And I'll have a 9 minus 24, which will give me a -15. Now we have our system in upper triangular form, so we should be able to do back substitution and solve. So starting with the -5z equals -15, we know z is equal to 3. Going to our second equation, 8y plus 7 times z, which we now know is 3, we can solve this equation. And we're going to get y equals negative 3. And finally, going back to the first equation and plugging in our values for y and our values for z, we should be able to solve for x. So our solution to this system of equations, written as an ordered triple, is 5, negative 3, 3. Now it's nice if there's one particular point that's a solution. Sometimes you'll find there are no solutions, and sometimes you'll find there are infinite solutions. What'll happen when you're doing that is you're going to have an equation, ax plus by plus cz equals d, and then another equation, ey plus fc equals g, let's say. But then in your third equation, you'll wind up getting 0 equals 0 after doing the operations. When that happens, that means that there are infinite solutions. And I'll show you on Friday a way to write an ordered triple which represents all those infinite solutions. On the other hand, if you wind up getting something with your last equation like 0 equals 5, then that tells you that there's no solution to this system.